Hello again, grade 8s. In today's lesson, we're going to continue to look at calculating the probability of independent events, although we're just going to look at some problems that are a little more complicated to the ones that we dealt with last time. So we can jump right into an example. We don't need to go through any notes. We've already gone through all the theory in terms of how we do these calculations. So what we have is a spinner is divided into 3 equal regions, as shown in the diagram below. A student is going to spin that spinner, and then they're going to roll a 6-sided die. So the spinner is going to be event number 1, and the 6-sided die is going to be event number 2. So let's start off by first of all drawing a tree diagram to represent the sample space. Okay, so let's pull up my pen. And so for a tree diagram, let's start off by writing down the names of the different outcomes. So we're going to do the spinner first. You can underline that or attempt to underline it. And then we have our die. And then we're going to write down, so this is part A. I'm going to write down our 3 different outcomes. So on the spinner, if you look at it, there's 3 equal regions. You can either land, the spinner can land on a region that has the number 1, region that has the number 2, or a region that has the number 3. Okay, so I'm going to write down 1, I'm going to write down 2, and I'm going to write down 3. So those are the trunks of my trees, the different outcomes for event number 1. And then from the trunk, you're going to branch into the outcomes of event number 2, which is going to be the die. Okay, so this could turn into 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, and then 1 and 6. It's almost impossible to draw a straight line using a drawing tablet. Okay, and then for this one, you could spin a 1 and roll, spin a 2 and roll a 1, spin a 2 and roll a 2, spin a 2 and roll a 3, spin a 2 and roll a 4, spin 2, roll a 5, and then spin 2, and then roll 6. And then we could also spin a 3 and roll a 1, spin 3 and roll a 2. These events are called independent because whatever you spin in the spinner doesn't have any effect on what happens on the die. Okay, and the final outcome would be spinning 3 and then rolling a 6. Okay, so that's my tree diagram. It was pretty messy. I mean, if I was doing this on paper, I'd probably use a ruler to draw the branches, but whatever. It's good enough. It communicates the point. Okay, B. It says, calculate the probability of obtaining the same number on the spinner and the die. Okay, so let's go to the next slide and just start to set up my calculations here. So let's do B. Okay, and we want to calculate the probability of obtaining the same number on both the spinner and the die. And that's equal to your number of favorable outcomes divided by your number of possible outcomes. I like to identify how many possible outcomes there are first. So the number of possible outcomes would just be count the total number of branches. You'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I have 18 possible outcomes. Now, the favorable outcomes would be obtaining the same number on the spinner and the same number on the die. Okay, so that would be 1 on the spinner and 1 on the die. That would be 2 on the spinner, and that would be 2 on the die. That would be 3 on the spinner, and that would be 3 on the die. So there's 3 possible outcomes where you could get both the same number on the spinner and the same number on the die. Okay, so now we can perform this calculation because the number of favorable outcomes is going to be 3. 3 ways you can obtain this. Now, 3 divided by 18 is going to give you a repeating decimal number. So you're going to have 0 decimal. If I calculate it, 1, 6, and the 6's just keep repeating. 1, 6, 6, 6, 6, dot, dot, dot. Okay, so we're gonna have to round here. And again, what I would typically do is round to the nearest thousand. So the nearest thousand means you're gonna round to the 3rd decimal place. To round to that 3rd decimal place, you have to look at what number is going to be in the 4th decimal place. Now, if that number in the 4th decimal place has digits 0 through 4, you don't round the 6. It just stays as a 6. But if it's digits 5 through 9, then you do round it. So in this case here, we're actually going to round that 6 up to a 7. So this would turn into, so this would be equal to 0 decimal, sorry about that, 1, 6, 7. And then turn it to percentage, move the decimal spot 1, 2 units to the right, or multiply by 100. They both do the same thing. So this would be 16.7%. Okay. It says also calculate the probability of obtaining a number on the die that is larger than the number on the spinner. Okay, so again, let's set up our calculation. We'll go back and actually figure out what this is. So we'll say the probability of obtaining a number on the die that is bigger than a number on the spinner. That's going to be equal to the number of favorable outcomes divided by the number of possible outcomes. The number of possible outcomes doesn't change. It's still 18. Okay, so let's figure out the number of favorable outcomes here. So let's choose purple. Okay, so I need a number on the die that's bigger than the number on the spinner. Okay, now if you look at this one here, so if you spin a 1, which numbers on the die are bigger than the number on the spinner? Well, let's underline them. 2, 3, 4, 5, and 6. Okay, so those are all bigger than the number on the spinner. How about if we spun a 2? Which numbers on the die are bigger than the number on the spinner? Well, that would be 3, 4, 5, and 6. And if we spun a 3, how many numbers on this die are bigger than the number on the spinner? That would be 4, 5, and 6. Okay, so if I count all these underlines here, this would show me the number of ways you can get a number on the die that's bigger than the number on the spinner. So I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then you'd have 12. So there's 12 ways you can obtain this. So let's change this to 12 over 16. 12 over 16 is also going to be a repeating decimal. So it's going to be 0 decimal 6, 6, 6, 6, and the digit 6 just does not stop repeating. So once again, the way to round it is we'll try to round to the nearest thousandth. So that's 1, 2, 3 decimals. We have to look at that 4th decimal to determine how to round. Since that 4th decimal is a digit that is 5 or bigger, it's a 6, we are going to round that 6 in the thousandths position up to a 7. So that's going to turn into 0 decimal 6, 6, 7. And if you multiply by 100, this would be 66.7%. Okay. So it's actually good. It's a good chance of you actually obtaining a number on the die greater than the spinner. Okay. Now, this is where it starts to get a bit weird. So it says, construct a 3rd column in the tree diagram and determine all possible sums. Okay, so we're going to go back to the tree diagram now, and I'm going to make a 3rd column. So, oops. This 3rd column, I'm going to say, is going to be the sum of the numbers. Okay, the sum of the numbers just means take the number on the spinner and add it to the number on the die. Okay, so 1 plus 1 would be a sum of 2. 1 plus 2 would be a sum of 3. 1 plus 3 would be a sum of 4. 1 plus 4 would be a sum of 5. 1 plus 5 would be a sum of 6. 1 plus 6 would be a sum of 7. Okay, go to this next tree. So a sum of 2 and 1 would be 2 plus 1 is 3. Oops. 2 plus 2 would be 4. 2 plus 3 would be 5. 2 plus 4 would be 6. 2 plus 5 would be 7. And then 2 plus 6 would be 8. 3 plus 1 would be 4. 3 plus 2 would be 5. 3 plus 3 would be 6. 3 plus 4 would be 7. 3 plus 5 would be 8. And then 3 plus 6 would be 9. Okay, so those are all the different possible sums you could get if you spun the spinner and rolled the die and you added the numbers on both the spinner and the die together. A lot of board games deal with that. Like you're playing Monopoly, for example. Like you roll like 2 6-sided die, and you actually it's the sum that tells you how many spaces you can actually move forward by. Okay, now what does it want us to do? Okay, so we did C. Now it says calculate the probability of obtaining a sum that is greater than 6. Okay, so let's set up the calculation in part D here. So I'm going to say the probability of obtaining a sum that is greater than 6. That's going to be equal to the number of favorable outcomes over the number of possible outcomes. Okay, look here, we still have 18 possible sums, 18 possible outcomes. So we can fill it in, 18. Now, how many sums have a number that's bigger than 6? Okay, so this is not greater than or equal to 6. It is just greater than 6, which means that 6 is not allowed. Okay, so let's highlight all the sums that actually would meet this, this criteria. Okay, so greater than 6. Okay, so greater than 6 means like 2, 3, 4, 5 are not in that category because they're less than 6. And greater than 6 does not include 6. So this would be 7 here. This would be the 7 here. It would be this 8. And over here, it would be this 7, this 8, and this 9. Those are all sums that are greater than 6. So how many total sums are greater than 6? 1, 2, 3, 4, 5, and 6 of them. Okay, so it's going to be 6 out of 18 is going to be my fraction. There's 6 favorable outcomes here. Okay, that is also going to be a repeating decimal number. So this will give me 0, decimal, 3, 3, 3, 3, 3, dot, dot, dot. Now, in terms of the rounding, and again, we're just going to stick with the rule, round to the nearest thousandth. If you do that, it's going to set up the percentage to be like rounded correctly. Okay, so round to the nearest thousandth, which means the first 3 decimals, and we have to look at the 4th decimal to determine how to round. Now, since the 4th decimal is a number that is the digit 3, we don't round that up. Okay, we only round up if this following digit is 5 through 9. So that's going to keep the thousandths digit to stay at a 3. So this would then turn it into equals 0, decimal, 3, 3, 3. And if you turn that into a percentage by multiplying by 100, we're moving the decimal spot 2 units to the right, you get 33.3%. Okay, a little bit more complicated because of an example, because we actually had to, in the tree diagram, construct an additional column to do some other probability calculations, which is why I wanted to leave for part 2, just because I felt like this example was a bit tougher. And that's it for this lesson. So in the probability workbooklet, you can complete the assignment that's called Probability of Independent Events, part 2. And then I will talk to you in the next lesson.